Hello and welcome. Today in this video we are going to learn about calculation of work. So how work is calculated for different types of forces, for different possible cases where we need to calculate work, and that's going to be the topic of this video. So let's get going. You can see on your screen that we are now first discussing the work done by a constant force. So when there is a constant force acting on an object, this is the simplest case of calculation of work. Let's consider a building that's of height h, and we throw a projectile of mass m from the top of this building and it lands on the ground below. Now in this kind of a case where the force is constant, now the force here is the force of gravity, which has a constant magnitude, mg in this case, and is always directed vertically downward. So this force has a constant magnitude, it has a constant direction, and therefore its work done is easiest to calculate. Now it's simply, for a constant force, work done is going to be F dot S. So you simply calculate Fs cos theta and you get your work. But let's simplify this a little bit. Even if the path is a curved path, the same thing still works, as long as the force is a constant force. So let's have a look. The particle, when we threw it, it goes on a parabolic path, as we studied in projectile motion. The force of gravity on the particle is mg, that's vertically downward, and there's a small displacement ds that we are considering for the particle. Now during this small displacement ds, the work dw that gets done is mg times ds cos theta. Now ds cos theta, if you look at the magnified view here, that ds cos theta is vertically downward. So what I do is I take ds cos theta to be dh, a small change in the height, and then the work dw comes out as mg dh, and when we integrate mg dh, mg is constant, it comes out of the integral, dh is integrated, and dh integrated gives us h, and therefore the work done comes out mgh. Now mg is the vertically downward force, and h is the vertical component of displacement, and we've got our work as a product of the magnitude of force with the component of displacement in the direction of that force. So that's kind of your mental calculation of work when the force is a constant force. It has to be, mind you, it has to be constant in terms of both magnitude as well as direction. So remember, the work done will be product of magnitude of force with the component of displacement in the direction of force. It can be positive, it can be negative, and the sign is easy to judge. Look at the force and the displacement, total displacement S in the motion. If the angle between the force and the displacement S is an acute angle, then the work done will be positive, and the angle, if the angle between the force and the displacement is an obtuse angle, then the work done will be negative. Because you very well know that the cosine or cos of acute angles is positive and cosine of obtuse angles is negative. Work involves Fs cos theta, right? So cos theta, if it is positive, work done is positive. If cos theta is negative, work done is negative. Now in our next example, we are going to learn how to calculate the work done by a variable force. Now it's still we are still keeping things a little simple. The motion is along a straight line, x-axis, we'll call that straight line the x-axis to keep things simple for us. So this force here has a magnitude f, which is a function of x. So it's this f has been shown as a function of x. There's a tiny displacement dx we are considering, and therefore the work dw done in this tiny displacement is fx times dx. Now when you substitute fx and dx in this expression, please make sure you remember one thing. Fx and dx must both be substituted in this expression along with their proper signs. So if if the force is in positive x, you substitute it as positive. If the force is in negative x, you substitute it as negative. And the same for dx. If dx is in positive x, you substitute it as positive. And if dx is in negative x direction, you substitute dx as negative. So work done comes out as the integral now of fx dx from the initial point xi to the final point xf, right? Now this work is a simple integral, and of course you know that this integral can also be evaluated as the area under the graph of f versus x. So if you're given a force, just draw a graph representing the force versus x and calculate the area under that graph, and you will still end up getting the same amount of work. Now let's take a simple example here. The example where we are taking a force fx, that's 2x squared, and we'll be calculating the work done by this force in moving an object from x equal to 1 to x equal to 2. So the work dw is 2x squared dx. The force is in positive x, dx is in positive x, so both are positive. So we have 2x squared dx. dw is dw is 2x squared dx. W is the integral of the same quantity. So 2 comes out of the integral being constant, and you integrate x squared dx from 1 to 2, which gives you 2x cubed by 3. Limits being 1 to 2, you substitute those limits and you end up with 14 by 3 joule, and that's the final amount of work that you get. So that's the work done by a variable force which is along a straight line. Let's take another very important example here, that of the work done by a spring, or the force that a spring applies. So we now have in this diagram here a spring which has a natural length L0 and it has a spring constant K. Now we extend this spring along the x-axis, and we'll be calculating work done by the force that the spring applies from the initial position where x equals xi to the final position where x equals xf. So let's calculate dw. Once we've extended the spring by x, the force that the spring exerts is minus kx, and the displacement we are looking at dx is in the positive x direction, so we substitute them in the formula. Fx times dx, fx is minus kx, dx is plus dx, and therefore dw comes out to be minus kx dx. W therefore will be, the integral of minus k times x dx integrated from xi to xf, and that's equal to minus half k xf square minus xi square. If you take the minus sign inside the bracket, you end up with half k xi square minus half k xf square, where xi and xf are the initial and final extensions of the spring. You should remember this expression as a formula for calculating work done by a spring, because spring questions are asked very, very frequently. So you can of course do the same thing graphically as well, as you can see on your screen. The same work can be calculated graphically. Just draw a graph of f equal to minus kx, f versus x graph, and take the area under the graph from xi to xf, and this little task I'm leaving for you to do on your own. And we now move on to the calculation of work done by a variable force. Now we've calculated work done by variable forces when motion is along a straight line. Now we look at a more general case where the force is variable and the motion is also along a curved path. Now in such cases we need the force and the path both well defined so that work can be calculated. So here the force is given as xi cap plus yj cap and the path is y equals x square, and we'll be calculating work done in moving along the path from the point 0, 0, that's the origin, to the point 1, 1. So now to calculate this work, let's consider a tiny displacement dx along this path. This dx of course equals dxi cap, the vector ds equals dxi cap plus dy j cap, and the force of course has been given to us as xi cap plus y j cap. Now looking at the path, the equation of the path y equals x squared, let's differentiate with respect to x so that we can get a relation between dy and dx. So differentiating, we get dy by dx equals 2x, and therefore dy equals 2x. Now what we do is, in the expression for ds, we substitute dy as 2x dx, and therefore we get ds equals dxi cap plus 2x dx j cap. This dy now is 2x dx. The tiny displacement vector ds becomes 2x dxi cap plus 2x dx j cap. F, if you remember, it's xi cap plus yj cap, and y can be substituted as x square, so f equals xi cap plus x squared j cap, and ds equals dxi cap plus 2x dx j cap. So what we've done is we've converted everything into x, which keeps things simple for us. This may not always be possible, but we've been able to do this here, and at neat and j level, this is about the maximum we expect anyway. So we have f now as xi cap plus x squared j cap, and ds as dxi cap plus 2x dx j cap. dw, the tiny amount of work now done, is the dot product of f and ds. So we take that dot product of f with ds, and we get x dx plus x squared plus 2x, x dx plus x squared into 2x dx. So we've got dw here, and once we have dw, what's next is we need to calculate the integral of this quantity x dx plus 2x cubed dx. The work now will be the integral of x dx from 0 to 1 and integral of 2x cubed dx from 0 to 1. This integral gives us x squared by 2 from 0 to 1 plus 2x to the power 4 by 4 from 0 to 1, and on substituting the limits we end up with the amount of work that gets done here, which is 1 joule. So you can substitute these limits and end up calculating the work. Thank you so much for watching this video. I hope you had some fun here, enjoyed this discussion on calculation of work. In our next video, we will be discussing about potential energy, various types of forces which fall into different categories as far as work done is concerned, and also we'll be discussing about potential energy, mechanical energy, and the conservation of mechanical energy. So thanks for watching. Keep enjoying these videos, keep liking them, sharing them, and subscribing to this channel. Thank you so much.